Hello, we continue our discussion on the interpretation of international tables page, and in this part we will look at the symmetry operations. So, one of the important information which is there in the international tables is the so called symmetry operations. After all, if you think what is a space group? So, a space group is a group of symmetry operations of a crystal. So, the symmetry operations in the sense is one of the most important information. The way the symmetry operations are discussed, actually there are two ways, and one of them diagrammatically where the symmetry elements are shown. There is a slight difference between symmetry element, geometrical symmetry element and symmetry operations. We will look at that. So, these diagrams show the symmetry elements, geometric symmetry elements. We are in the space group 66 and the space group Hermann-Mauguin symbol for the space group is capital C followed by two small c's and m. So, the capital C is C centered lattice and the small c's are showing that there are glide operations, C glide operations perpendicular to A and B axes, and there is a mirror plane perpendicular to the third axis, that is the C axis. So, that is the space group we are in. We have discussed the symmetry element diagram in little bit detail in a previous video, and now we will look at this block, this particular block which is called the symmetry operations, this block. And this block has, you can see there are two parts, two sub blocks to this. One is for set 0 0 0 and another is for set half half 0. That is because this is a C centered lattice. The second block half half 0, as you can see, is the centering translation for this particular lattice. So, 0 0 0 is the origin, you can say, and half half 0 is the centering translation. You can see that there are 8 operations listed in both the sub blocks, and they are numbered 1, 2, 3. They are serially numbered up to 8 in the first block, and then again 1, 2, 3 to 8 in the second block. And each of these, the details associated with these serial numbers are details about the symmetry operation present in the space group. So, we will like to look at how to read the information about symmetry information given in this symbol. So, let us look at it. We will look at it one by one carefully. So, to do that, let me try to put the symmetry element diagram and the symmetry operations list close to each other, which I have done here, and let us look at one by one. So, in the first block, in the first set, the 0 0 0 set, the first symmetry operation given is just 1, and as you know, 1 represents identity, and that has to be there in any symmetry group. That is the requirement of the group property. Every group has to have identity as one of its symmetry operation. So, our space group also has this identity. Of course, identity cannot be represented by any geometric symmetry element. So, it is not there in the diagram, we just have to assume its presence and we have to know that it exists. So, 1 is the identity. Let us now come to the second operation, the second list, which is written as 2 and then O comma O comma Z. So, what is this showing? So, the first letter 2, the first number 2 is, so let me write it here. We are talking of the operation 2 with the information 2 and then 0 comma 0 comma Z. So, this 2, the first 2 is telling us that it is a rotation, a two-fold rotation, that is a rotation by 360 degree by 2, that is 180 degree. So, it is a 180 degree rotation. The next 3 numbers and letters, the triplet OOZ, tells us about the rotation axis. So, 00Z is the rotation axis. Now, you can see that the two of the coordinates are 0, means x is 0 and y is 0, and z is left as a variable. So, all points for which x is 0 and y is 0, but z can take any value is the rotation axis, which means this itself is the z axis. So, that means this symmetry operation 2, which we are discussing now, is a two-fold rotation, a 180 degree rotation about the z axis, passing through the origin and parallel to the z direction. So, similar information is there. There are other two-fold axes represented as operation 3 here, and then there is an operation 4 there. So, all these are two-fold symmetry operations. Then operation 5 you can see is a 1 bar. 1 bar is an inversion, and for inversion center the coordinate of the inversion point is given. In this case it is given as OOO, which means it is origin. So, you have an inversion about an origin. So, let us relate these to symmetry element diagram. So, the operation 2 which we discussed was the two-fold parallel to the z axis. So, that was the operation 2, and then this operation 5, which is the inversion center in the origin, is just the dot inside the lens, that is the operation 5. Let us look at operation 6. The symmetry operation 6 is shown as M and then x comma y comma O. M represents a mirror reflection. So, this is a symmetry operation which is a mirror reflection. Let me write it here, 6 M So, this represents reflection. So, it is a reflection operation, and if it is a reflection operation, we need to give the plane of reflection, the mirror plane, and that is being given by this triplet x, y, O. So, z coordinate is fixed 0 and x, y is left variable. So, that means it is a x, y plane passing through the origin. So, there is a mirror reflection in the x y plane passing through the origin. The x y plane, the mirror plane, is what is being shown here by this symbol here. So, that is the representative of operation 6. So, you can see I am saying it is representative of operation 6, it is not actually the operation. What is shown in the diagram is not the operation, but the symmetry element or the geometric symmetry element associated with the operation. And what is being shown in the table here below it are the representations of the operation, that what. So, M represents here in number 6, M represents the reflection operation, and x comma y comma o represents the x y plane, which is the geometric symmetry element, and it is only the symmetry element which is finally shown in the diagram. An interesting thing to note here, when we come to the second block, the half of 0 set. So, the first operation now is T half of O. T represents the translation, and as you know, this is a C centered lattice. So, there is a half of O translation available in this lattice or in this space group. So, that is the first operation, is the translation in the second block. So, this second block is given as half of O plus set, which means for every position you have to add this half of O to get to the new position described by this set. So, identity does not do anything. So, identity represents the position somewhere in this space group, and then the so that is the number 1 of the first block, the OOO block, but the number 1 of the second block is the translation half half O. So, these numbers are given the same numbers in the two blocks because they are correlated. So, the number 2 in the second block is representing a symmetry operation in which corresponds to the symmetry operation of the 2 of first block. Let me write it this way. So, these, for example, these twos, in fact, a more interesting case which I will like to handle and discuss with you is the two operations which are listed as 6 in the first block and 6 in the second block. So, what does it mean is that these two operations listed as 6 are related to each other if you add a translation to the operation 6. If you add the half 0 translation, the C centering translation to the operation 6 of the first block, you will get operation 6 of the second block. Let us see how does that happen. So, the first block, the number 6 we have already seen here, is a mirror x y 0, but the same number 6 in the second block is being shown as in glide, and for glide operation, glide always is associated not only with a mirror plane, but also with a glide vector. So, the representation of glide operation is given by the symbol for the glide. Here it is n, which is symbol for diagonal glide. N is diagonal glide, and this is the glide translation. And finally, you have the glide plane. So, if the mirror is there, there is no glide translation. So, you only give M and the glide and the mirror plane, but when you represent the glide operation, you have to give the symbol for the glide, which is N here, then the glide translation, which is half 0, and then the glide plane, which is x y 0. So, this is also the x y plane. So, note this interesting thing. The x y plane, is present in this operation 6 in the second block, and there it is being shown as an n glide operation, a diagonal glide operation. This x y plane is present in the operation 6 in the first block also, but there it is shown as a mirror, a reflection. And if you see in the xy0 plane, the symbol which is shown here is only for the mirror, not for the n glide. So, how is means this can be little confusing, but the clarity will come once one distinguishes between the geometric symmetry element and the symmetry operation. What is shown in the diagram, this particular line at 90 degrees, which is showing a mirror plane parallel to the xy plane. So, this is a mirror plane which is a geometric symmetry element, and the same mirror plane is present in these two symmetry operations, which means there are more than one symmetry operations which can be associated with the same geometric symmetry element. Let me try to write this for greater emphasis. So, one has to distinguish between geometric symmetry element, which for both the operation is a plane, and in this case it is an xy plane represented as xy0. But this geometric element is associated with more than one symmetry operations, and in this case symmetry operation 6 for the 0 plus block, you get an operation 6, in which case it was a mirror reflection. So, it was a mirror reflection, and when we looked at half of 0 block, that is the same operation with centering translation, it became an n glide operation. So, these are symmetry operation, both of these are symmetry operations or let me call it different symmetry operations associated with the same geometric element. In fact, if you have a mirror plane in a space group, if you have a mirror plane, then there are also infinitely many translations parallel to the mirror plane. In this case, in this particular example, is a half of 0 translation which is parallel to the mirror plane. The mirror plane itself is the xy plane. So, if there is an object which is operated upon by the mirror, so it reflects in the mirror and comes here, and then it translates by the translation vector, because translation vector also is part of the space group. So, that will act. So, mirror is there, so you get that object. Let me call this 1, or let me call this A, let me call this A, let me call this B, which results from mirror, and now I translate it and I get the object C due to the translation. So, if you now relate A directly to B, it is a combination of reflection followed by a translation parallel to the mirror plane, and since the translation vector is half of 0, this is called a diagonal glide or n glide operation. And this particular operation, so this was the n glide operation, and this operation directly reflecting here was the reflection operation. So, both are given this number 6 because the two are related. One was without the half of 0 translation. So, that is in the OO plus group. The another is with half of 0 translation. So, that is in the half of 0 plus group. So, I think we have discussed in quite a bit detail the symmetry operation. Other symmetry operations which I have not explained, you can try to work out and correlate with the symmetry element diagram which is also present. Thank you very much.